The speed of light. A surprising discovery with Richard Feynman. There's something strange about the universe, something so fundamental that once you see it, you can't look at space and time the same way again. It's not about mystery. It's not about magic. It's about a simple fact that took centuries to understand. Light moves at a specific speed, not approximately, not on average. Exactly. And that speed appears to be the same no matter how you measure it, no matter how fast you're moving when you measure it. This sounds like a small detail. But when physicists took it seriously, really seriously, the entire structure of space and time had to be rebuilt from the ground up. Tonight, we're going to walk through that discovery. We'll start with falling objects. We'll end with the fabric of space-time itself. And along the way, we'll see why Richard Feynman called this one of the most beautiful insights in all of physics. Let's begin at the beginning. For most of human history, motion was divided into two categories. There was motion on Earth. Rocks fell, arrows flew, carts rolled down hills. All of this seemed chaotic, temporary, imperfect. And then there was motion in the heavens. The moon circled, the planets wandered, the stars turned in perfect circles night after night. This motion seemed eternal, divine, governed by completely different rules. Galileo began to challenge this division. He noticed that when you drop a heavy object and a light object from the same height, they hit the ground at the same time. Air resistance confuses things, but in the absence of air, a feather and a hammer fall together. This was the first hint that motion follows rules. Consistent, testable rules. Isaac Newton went further. He realized that the moon is falling. Not falling down, but falling sideways. It's constantly being pulled toward Earth, but because it's moving sideways so quickly, it keeps missing. That's what an orbit is. A continuous fall that never ends. And here's the crucial step. Newton showed that the same force that pulls an apple to the ground also pulls the moon toward Earth. The same mathematical relationship, the same inverse square law, one equation describing motion everywhere. This was unification, Earth and sky, subject to the same laws. But Newton's laws had a hidden assumption. They assumed that time is absolute, that a second is a second, everywhere, for everyone. And they assumed that space is absolute, that a meter is a meter, regardless of who measures it or how fast they're moving. These assumptions seemed obvious, but they were wrong. The first crack in this picture came from something unexpected: the speed of light. For a long time, people assumed light was instant. You open your eyes, you see? No delay, no travel time. Galileo tried to measure the speed of light by standing on one hill with a lantern while an assistant stood on another hill. Galileo would uncover his lantern, the assistant would see it and uncover his own lantern, and Galileo would measure the delay. But the delay was too small. Human reaction time overwhelmed any signal. The breakthrough came from astronomy. In the 1670s, a Danish astronomer named Ole Romer was studying the moons of Jupiter. He was timing their eclipses, the moments when they passed behind Jupiter and disappeared from view. He noticed something odd. When Earth was moving toward Jupiter, the eclipses happened slightly earlier than predicted. When Earth was moving away from Jupiter, the eclipses happened slightly later. The moons themselves weren't changing their orbits. The difference was the time it took light to cross the changing distance between Earth and Jupiter. Romer calculated that light must be traveling at a finite speed. It wasn't instant. It was fast, extraordinarily fast, but not infinite. This was the first measurement of the speed of light, and it revealed something profound. Light is a physical phenomenon. It propagates. It takes time to get from one place to another. Over the next 2 centuries, measurements got better. In the 1800s, scientists began measuring the speed of light in laboratories, not just through astronomical observation. They used rotating mirrors, spinning gears, carefully timed pulses, and every experiment gave the same result. Light travels at about 300,000 kilometers per second in a vacuum. But then something deeply strange emerged. Imagine you're standing on a train platform. A train passes by at 50 kilometers per hour. Someone on the train throws a ball forward at 20 kilometers per hour relative to the train. How fast is the ball moving relative to you, standing on the platform? 70 kilometers per hour. You add the speeds. This is intuitive. This is how velocities work in everyday life. Now replace the ball with a beam of light. The train is moving at 50 kilometers per hour. Someone on the train shines a flashlight forward. The light moves at 300,000 kilometers per second relative to the train. How fast is the light moving relative to you on the platform? You'd expect 300,000 kilometers per second plus 50 kilometers per hour, a tiny bit faster. But that's not what happens. When you measure the speed of that light, you get exactly 300,000 kilometers per second. The same speed, not faster, not slower. This was verified experimentally in the late 1800s, most famously by Albert Michelson and Edward Morley. They built an interferometer, a device that could detect incredibly tiny differences in the speed of light in different directions. Earth is moving through space. It's orbiting the sun at about 30 kilometers per second. So if light travels through some medium, some cosmic background, you'd expect light moving in the direction of Earth's motion to be slightly faster or slower than light moving perpendicular to it. But Michelson and Morley found no difference. Zero. Light had the same speed in every direction, regardless of Earth's motion. This result baffled physicists. It made no sense. Speeds are supposed to add. That's how motion works, unless something else is going on. Albert Einstein took the experimental result seriously. He didn't try to explain it away. He didn't invent invisible mechanisms to preserve the old picture. He asked a different question. What if the speed of light really is the same for everyone, no matter how they're moving? If that's true, something else has to give. What gives is time and space. Here's how Einstein thought about it. Imagine you're on a train, holding a flashlight. You point it at the ceiling and turn it on. The light goes up, bounces off a mirror on the ceiling, and comes back down. You measure the time it takes. Call it 1 second. Now imagine someone standing on the platform, watching the train go by. From their perspective, the light doesn't just go straight up and down. It follows a diagonal path, because the train is moving forward while the light is traveling. The diagonal path is longer than the straight path. But light has to travel at the same speed for both of you. That's the experimental fact. If the path is longer and the speed is the same, then the time must be longer. The person on the platform sees your clock ticking slower. Not because your clock is broken, not because of some mechanical effect, but because time itself is passing differently for you than for them. This is time dilation. Moving clocks run slow. Not metaphorically, actually. And there's a companion effect. Moving objects are compressed in the direction of motion. This is length contraction. A meter stick moving past you is shorter than a meter stick at rest. These aren't illusions. They're not perceptual tricks. They're real changes in the structure of spacetime. Space and time are not absolute. They're not fixed, universal stages on which events happen. They're flexible. They depend on motion. And this flexibility is exactly what keeps the speed of light constant for everyone. So we've established that nothing can move faster than light relative to any observer. But why? What stops you from just pushing harder, adding more speed, going faster and faster until you break through? The answer is energy. When you push an object, you're adding energy to it. In everyday life, that energy becomes motion. You push a cart, it speeds up. Push harder, it goes faster. But there's a subtlety. As an object moves faster, it becomes harder to accelerate. Not because of friction, not because of air resistance, because of the structure of space-time itself. Here's the way Feynman liked to explain it. When you add energy to an object, that energy doesn't just increase its speed, it increases something deeper, its resistance to further acceleration. At low speeds, this effect is negligible. You don't notice it pushing a shopping cart. But as you approach the speed of light, the effect becomes enormous. Imagine accelerating a particle in a particle accelerator. You pump in energy. The particle speeds up. You pump in more energy. It speeds up a little less. You keep pumping in energy. The particle gets closer and closer to the speed of light, but it never quite reaches it. To actually reach the speed of light, you'd need infinite energy. That's not a practical limitation. That's a fundamental limit built into the laws of physics. And this is why light itself can travel at light speed. Photons, the particles of light, have no mass. They don't have inertia in the usual sense. They're born moving at light speed, and they can't do anything else. But anything with mass, anything that has a rest frame, a state where it's not moving, can never reach light speed. It can get arbitrarily close, but it can't get there. This isn't a barrier in space. It's a limit on how spacetime allows cause and effect to propagate. And that brings us to the deeper point. The speed of light isn't really about light. It's about causality. It's about the maximum speed at which anything can influence anything else. If you turn on a flashlight here on Earth, the light spreads outward at 300,000 kilometers per second. Someone on the moon sees it about a second later. Someone on Mars sees it minutes later. Someone in another star system sees it years later. But this isn't just true of light. It's true of everything. Gravity propagates at the speed of light. If the sun suddenly vanished, Earth wouldn't immediately fly off into space. It would keep orbiting for about 8 minutes, the time it takes for the change in the gravitational field to reach us. Information propagates at the speed of light. You can't send a signal, any kind of signal, faster than light. You can't use gravity or quantum entanglement or any clever trick to beat this limit. The speed of light is the speed of cause and effect itself. This has profound implications. It means the universe has a structure. Events that are far apart in space can't influence each other instantly. There's always a delay, a light travel time, a gap between cause and effect. This structure is what makes time meaningful. If causes and effects could be mixed up, if future events could affect the past, the notion of time as an ordered sequence would break down. The speed of light holds it all together. This isn't abstract philosophy. We see this limit in real experiments every day. Particle accelerators like the Large Hadron Collider routinely accelerate protons to 99.9999% of the speed of light. The protons are moving so fast that they circle the entire 27-kilometer ring over 11,000 times per second. At these speeds, time dilation is dramatic. From the proton's perspective, the journey around the ring takes much less time than it does from our perspective. The protons are experiencing time more slowly, and despite the enormous energy being pumped into them, they never quite reach light speed. They asymptotically approach it. The closer they get, the harder it becomes to go faster. GPS satellites provide another example. These satellites orbit Earth at about 14,000 kilometers per hour. Not fast compared to light, but fast enough that relativistic effects matter. The clocks on the satellites run slightly faster than clocks on the ground because they're experiencing weaker gravity. But they also run slightly slower because they're moving. These effects partially cancel, but the net result is measurable. If GPS didn't account for relativity, the system would accumulate errors of several kilometers per day. Navigation would be impossible. Every time you use a GPS device, you're relying on the fact that time and space are relative, that the speed of light is constant, and that Einstein was right. So let's take stock. We started with falling objects. We unified motion on Earth with motion in the heavens. We discovered that light has a speed, and that this speed doesn't change when you move. That single fact forced us to rethink everything. Time is not absolute. Space is not absolute. They're woven together into a single structure, spacetime, and that structure is flexible. The speed of light emerges as a fundamental limit, not on motion, but on causality. It's the maximum speed at which influence can propagate, the speed at which the universe permits cause and effect to unfold. Nothing with mass can reach this speed. The closer you get, the more energy you need, and the limit is infinite energy for the final step. But light itself, massless and pure, moves at exactly this speed. Not because it's trying to, but because it can't do anything else. There's something elegant about this. The universe has a speed limit, and that limit isn't arbitrary. It's baked into the structure of spacetime itself. Richard Feynman often emphasized that physics isn't about memorizing facts. It's about understanding relationships, seeing how different pieces fit together, grasping the logical structure that makes the universe comprehensible. The speed of light is one of those pieces. Once you see why it exists, why it's constant, why it's a limit, a dozen other things suddenly make sense. Time dilation, length contraction, the equivalence of mass and energy, the propagation of gravity, the structure of causality. All of these emerge from taking seriously the idea that the speed of light is the same for everyone. It's not magic. It's not mystical. It's just the way space-time works, and the fact that we can understand it, that we can measure it, that we can build technology around it, is remarkable. We live in a universe that has rules. Deep, consistent, elegant rules. And when we pay attention, when we measure carefully, when we think clearly, those rules reveal themselves. The speed of light is one of those revelations. A number, yes, but also a window into the structure of reality itself. And that's worth thinking about.